So let me start by introducing our speaker today, Professor Xin-Nian Wang. He got his PhD from Oregon University in 1989. He had a postdoctoral position from 89 until 91 at Lawrence Berkeley National Lab. From 90 to 92, he was also a postdoc at Duke University. After that, he joined Lawrence Berkeley National Lab as a divisional fellow and was there a fellow from 92 till 97. In 97, he became a senior scientist at LBL. During a period of 1999 to 2007, he was the head of nuclear theory program, and from 2010 to 2015, the manager and co-spokesperson of JET collaboration. He's also remaining the member of the JET collaboration now. From 2011 to 2017, he was also a 1,000-plant professor and director of the Institute for Particle Physics at the Central China Normal University in Wuhan. And from 2017, he's just a professor and the director of the Institute of Particle Physics at the same university in Wuhan. In 2002, he was elected a fellow of the American Physical Society with a citation for his contributions to the understanding of perturbative hard QCD processes, nuclear collisions at very high energies, especially the roles of gluon shadowing, multiple interactions, and jet quenching. So with that, I'll give the microphone to Xin-Nian, and you may start now.
Well, thank you, Igor, for inviting me to come here to give this online talk. And it has been a trying time for all of us, so I have to get used to this. Today I will talk about using JET as a tomography tool to study hot and cold nuclear matter. Since Igor reminded me this is a colloquial style, so I will start with some introduction about heavy ion interactions. We know that the strong interaction, QCD is the underlying theory for strong interaction. And the story of QCD is essentially the story of different symmetries and then their breaking or restoration in different scenarios. And for example, the SUC gauge symmetry gives rise property what we know today as asymptotic freedom at short distance, and by extension it also leads to this confinement at long distance when the strong coupling constant is becoming too large. We have also chiral symmetry breaking, and it's the restoration. In addition, we have also scale and UA anomaly, and those symmetry and the breaking believed to be responsible for most of the mass generation of strong interaction. So the study of many body problem, in particular the property of dense matter at extreme conditions, it is part of the story of the symmetry breaking and restoration at different temperature and density. And that leads us to this fascinating structure of the phase diagram of our strong interaction, and from this quark-gluon plasma at very high temperature, which is believed to only existed in nature at only a few microseconds after the Big Bang of early universe, to the possibility of the existence of quark matter at the core of a neutron star. And our normal nuclear matter sits right here. In addition, in recent years, there has been proposal of all kind of exotic phase, like color superconductor, quark-gonial matter, etc. At very high for the phase that is relevant for heavy ion interaction at extremely high energy, the most relevant equation of state is the quark-gluon plasma or the matter with almost zero chemical potential. Means there's no, you can neglect the net baryon number in the system. In that case, the equation of state for this matter has been studied by using lattice QCD to actually very high precision. So this is, for example, this is the calculation from this hot QCD collaboration, consists of people from Bielefeld, Brookhaven, and also CCNU in China. And first of all, you find that at zero baryon density, there is no actually a forced order phase transition. You have a very fast what they call crossover, and that crossover happens around 150 MeV temperature. And then if you go into even higher temperature, you find that the equation of state is still quite far away from the non-interaction Stefan-Boltzmann limit of ideal gas of quarks and gluons. So this indicates that even at very high temperature, the quarks and gluon plasma still have many non-perturbative features in the system. And this can be recently people propose can be studied as a part of the quasi-particle system mode at very high temperature. So to reach that high temperature, it was long proposed, actually very long proposed to collide heavy nuclei at very high energy. So in this case, by colliding these two heavy nuclei, you liberate a lot of quark particles, quarks and gluons from the vacuum, and you convert this kinetic energy of the beam essentially into a local temperature of the system, and hopefully you reach a confinement in that system. And so far we have come a long way from this proposal, and from early days like Bevlak at Berkeley studied this whole business to AGS and then RHIC and LHC, and finally we are at today. We also have the heavy ion experiments at the highest energy at CERN at LHC. So this quark-gluon plasma that you created by colliding heavy nuclei in a laboratory, and definitely they are very small. I mean, they're small size. They're probably, you can only reach the size of the heavy nuclei possible. So far, the heaviest nuclei we used is uranium, for example, and that is only about maybe 10, 12 Fermi in size, in diameter. And also it's very transient, because you create this in a vacuum, they essentially will disappear very quickly, also on the order of a few Fermi over C, maybe 10, maybe 20 Fermi over C. So to study the property of this quark-gluon plasma, one really have to resort to self-diagnosis system, like the signals that are coming from this quark-gluon plasma. So I want to categorize those diagnostics into 3 categories. The first one is what I consider the best one, actually, is the electromagnetic emission from the system. Since photons, for example, and electrons, they don't interact strongly with the quark-gluon plasma, so they can actually escape from the quark-gluon plasma almost unmodified. And using that, you can actually study the medium response to electromagnetic interaction. And for photons, they are virtual. For example, their resonance like Rho meson, phi meson, and even J psi. You can also study the modification for such resonance. And then occasionally, even though it's rare, you also produce very energetic partons by Rutherford scattering of the quarks and gluons inside nuclei, and they come out the system almost 90 degrees to your beam direction. And you can imagine that those energetic particles, what we call jet or quarks and gluons, they will also interact with the medium, and then they should be also modified. And finally, for the bulk, for the most of the particles that you produce in heavy ion interactions, they also expand, and then you can study the bulk properties by looking at the collective behavior of the system. So this is really a really long list of topics. And today, as you see from my title, I will only focus on the second, what we call jet physics, and using jet as a tomography to study this quarks and gluon plasma in heavy ion interactions. So what is quarks? I actually look back in the literature, and the first time the quarks were used was in the early 70s. The first one was proposed by people like the Groot and Ruijgrok. For example, they use this so-called uncorrelated jet model to describe hadron production in hadronic interaction, for example, in E plus minus. And only a couple of years later, and of course, Gross, Ruijgrok, and Politz discovered the asymptotic freedom of QCD. So lay down a foundation of QCD as a theory. You can actually do perturbative calculation when the coupling constant is small at very short distance. So around that time, people already have discovered there is this strange, jetty structure, for example, here in E plus minus there. And that leads to the discovery of what the glue degrees of freedom, 3 jet events, for example. So that led to a theory discussion by Alice and company and Georgia, for example. They produce using this partons production to describe this jetty structure. And only a year later, of course, Sturman and Weinberg wrote this seminal paper that essentially laid down the foundation for modern perturbative description of jet production and its property in QCD. So this work essentially laid down the foundation using a jet as a tool, a theoretic tool or experimental tool in high energy physics. And for example, if you discover any particles like Higgs top quark, you really have to rely on essentially their jet structure using jet as a tool. And the study is so precise, you can even use the jet production physics to determine the running coupling constant of strong interaction. So in heavy ion interaction, of course, among this interaction where you produce a hot quark-gluon plasma, and you also produce energetic quarks and gluons as a coincident. And so the idea is that we can use, actually, since we know the initial production is at short distance, that can be described by perturbed QCD. We know its production rate. So, and then you can measure its final production rate, and therefore you can infer how the jet is propagating through the quark-gluon plasma, and what is the energy loss. For example, what is the transverse momentum broadening? And that is essentially the basic idea behind this jet tomography. And it is essentially, you are just looking at all the hadron spectrum from the, from the heavy ion interactions. The high PD one, very energetic one coming from here, what we call high PD, essentially is used to probe the property of the bulk of the quark-gluon plasma at the small scale. And that's essentially the idea here. So to give you a very easy idea of what kind of property we're using as for jet is, let me start with the basic, when you consider electric charge, going through multiple scattering, for example. And we all know that, for example, when a charge is propagating through the vacuum, it carries, of course, its electromagnetic field with it. But once you actually, this charge scatter, it changes direction, for example. And the field itself has inertia. First of all, you have to shake off the field it carries with it. And then when it changes direction, it has to build up its electromagnetic field again. And this will essentially lead to what we know as the photon radiation. And it consists of the initial radiation by shaking its electric field, and also final state radiation when it's built up its field again. And the radiation from the initial state radiation and final state radiation, in fact, actually have the opposite phase. So when you calculate, for example, the photon spectrum, if you look at the photon radiation, the angular distribution, in the middle here, as we call it in the central here, you have a destructive interference, okay? And then after you integrate over the angle, you will get this beta Heitler, formula for the photon, for the photon intensity coming from this single radiation. And you can imagine that if you have multiple interactions, as your particle goes through the medium, you have multiple interactions. In this case, all you have to do is sum up all the radiation amplitude here, and what's new come in here, and then you have to really add the phase, because each radiation have different phase. You have to really add the phase when you sum up all the amplitude. And that's what's interesting physics comes in. And in the modern term, if you want to write this in terms of Lorentz invariant form, so you can write the photon invariant spectrum essentially as amplitude. This amplitude essentially is made of the photon polarization times the the current. This is the sum of the current from each scattering here. So this J here is essentially the current from each scattering, and then the total amplitude is the sum of all of them. So if you look at the phase difference between two scatterings, you can rewrite this in terms of the distance divided by formation time. We define formation time. Okay, at a small angle, this essentially is 1 over omega and theta squared. The theta is the radiation angle between the photon and the charge, the velocity of the charge. This is I'm talking about at very relativistic scattering here. And then in terms of this formation time, there's two limits. If the formation time is too long, it's very long, and much larger than the size of the system. For example, the multiple scattering here. And then in this case, you can essentially this is very like this is that size L over formation time is very small. You can neglect this phase, and then you sum of the coherent sum of all current. And then what happens is that all the current, the initial radiation, will be cancelled by the final state radiation of the last scattering. And at the end, the final result look like a radiation coming from a single coherent scattering. Oops. And it consists of the initial state radiation of the first scattering and final state radiation of the final scattering here. So everything look like a single scattering. But if this is what we call the factorization limit. But in the other limit, if the formation time is extremely small comparing to a neighbor scattering, the distance between two scatters here, and then you have to really sum all the radiation. It turns out that the interference here term, because of this, will completely just cancel out. And then what you have is essentially the intensity is an incoherent sum of Bethe-Heitler radiation spectrum. So in this case, the intensity is proportional to the number of scatters in your system. And then if you look anything in between, and you can divide the number of scatterings into a bunch, for example. And each bunch, the total angle you can consider is the Q square. This Q square is the transverse momentum broadening per scattering. So this is the Q square over E is essentially is angle per scattering, and then if you multiply by the number, this is the total angle broadening due to the multiple scattering. And then I define this number of scattering per bunch is that the total formation time here, if you multiply by the mean free path, the total length is around the formation time. So in the sense that all the scattering within this bunch are all coherent. And then between each one, you can consider them as the incoherent sum. So from here, you can calculate what is this number. And then the effective spectrum essentially is the total spectrum in the incoherent, as if everything radiate, and then divide by this number of scatter in per bunch, and then you arrive this effective spectrum for a charge propagating through a medium with multiple interaction. So this is actually this is what we call LPM interference, Landau-Parmov-Migdal interference. only after 50 years after it was proposed, it was finally actually confirmed, measured at SLAC when they shoot electrons through a nuclei. And this was like already 20 years ago. And what happens in QCD? The QCD is very, besides this 9 billion, it almost look like the same as QED, right? So you should also have the induced radiation like this initial and final. But since the glow exchange here carries color here, so the initial state radiation and the final state radiation, the color is different. So even though there's still interference between initial and final state radiation, the interference is not really complete. So you still have a finite, radiation amplitude after the, interference term. And in addition, we know that glue carries color, and it also have self-interaction. It also radiate. So you have to really sum this up together. So the end result is kind of interesting. If you look at the angular distribution, the angular distribution of glue radiation in QCD is very different from QED. In QED, you have this, this dip, and the radiation essentially is picked at initial and final particle direction. But in QCD, if you have two beams coming in, and this is the known that all particles have this plateau-like angular distribution, and this essentially is due to the non-abelian nature of gloom radiation. And then in 96 and BDMPS proposed that they look at this calculation, and they actually find out that if you want to calculate energy loss into multiple scattering, essentially it's dominated by this kind of glow multiple scattering through the medium. The final result is, the simple result is very, very interesting. Because of this 9 billion, this LPM effect, Landau problem interference, the total energy loss is proportional to the total length in a quadratic form. This is essentially purely coming from the LPM interference in 9 billion interaction here. And then it is also proportional to a quantity, this transverse momentum squared broadening per mean-free path. And this, we call it jet transport coefficient here. And that is actually what physics come in here about the properties of nuclear. Okay, so the simplest process where you can have the initial Parton production and also through multiple scattering is in deep inlet scattering of nuclei here. So here you scatter electron, and the electron kick out a quark from one nucleon, and this nucleon will go through the nucleus, and it will interact with another nucleon, for example. And this is the simplest rescattering in DIS. And from this scattering, there are many processes in perturbative QCD. It turns out this is the dominant diagram here. So essentially, it's a quark scattering of a photon, and it will scatter with another gluon from a nuclear, and the gluon will radiate another gluon here. And you can calculate this glue spectrum. In a recent paper, we find out that the glue spectrum is determined, of course, by this glue distribution. This is what we call transverse momentum dependent glue distribution from your nuclei, from your nucleus. And then you have the splitting function here, which looks like the vacuum here. And then you have this radiation amplitude, which has this LPM interference. Okay, this is LPM interference. And then the formation times here comes in. And in this static and soft radiation limit, this leads to people normally known as the Gelassi-Levin and Viteb GLV form of induced radiation of multiple scattering in this so-called iconal expansion or opacity expansion, the leading opacity expansion here. So if I consider the collinear limit, which means that the transverse momentum of the globe is larger than the transverse momentum of the globe here. So this is what we consider collinear limit. You can expand this. You can expand the K purple here. And then this leads to the simple formula for the energy loss on what we call high twist approach here. Again, I want to emphasize this energy loss is proportional to the Q hat. This is the transverse momentum broadening square per mean free path, and which is directly related to the glue density inside your medium. Okay, and this actually formula is sort of very universal. It can be applied to a cold nuclear. It can also be applied to quarks and glue plasma, quark-gluon plasma here. And that essentially is the property we are looking for when we study jet physics in heavy ion interactions. And in addition, you can also calculate the elastic energy loss, which is also related to this jet transport coefficients. But in general, especially for light quarks, glues, quarks, light quarks, this elastic energy loss is much smaller than the radiative energy loss, except for heavy quark. Especially for heavy quark at low energy, there the elastic energy loss become almost comparable to the radiative energy loss. That's only because for low energy heavy quarks, the radiation is essentially suppressed by its mass. But at the end, so essentially, if you can measure the Parton energy loss, you can extract the jet transport coefficient. But measure energy loss is quite difficult because we don't see Parton directly. So of course, the first idea is the fact that those partons essentially will eventually hadronize, become a hadron. So you want to study the final hadron spectrum in order to extract the Parton energy loss, and then get the jet transport coefficient here. And with this idea, essentially, you can reformulate this as a modified splitting here. You have a quark which interact with the medium, and you split to a glue and a quark, and you can find this modified medium-induced splitting function. And with this splitting function, together with the vacuum splitting, you can calculate the modified fermentation function. Essentially, the fermentation function is the hadron production, the spectrum of hadron coming from the hadronization of a parton. With this fermentation function, you can, calculate the final hadron production from either proton scattering or from heavy ion interaction. If you know the initial Parton distribution function, and we know the perturbative, cross-section, and you will be able to calculate this. So in this case, by comparing two experiments, and then you can extract the Parton energy loss and in this case the jet transport coefficient. So here I summarize the experiments coming from RHIC. For example, this idea was actually a success, and it was the first measurement coming from RHIC in about 2000. The jet quenching is so significant that you cannot really miss it. So here you not only see the suppression of single hadron spectrum here, suppression from one. The suppression this here is only, of course, relative. You simply compare the spectrum in heavy ion interactions to PP, to the PP elementary process in vacuum, and you look at the ratio between them and normalize, by number of binary PP scattering here. The ratio, if the ratio is 1, you don't have any suppression. If the ratio is below 1, you have a strong suppression. In fact, here you have a suppression of factor 5. You also have a suppression of dijet. Normally jet is produced back to back, and you trigger one, the other one has to go through the quark plasma. You see the dijet structure in PP in a vacuum, and in heavy ion interactions, the away side jet is completely suppressed. You also use a photon as a trigger. The photon, normally you produce a photon plus a jet. The photon normally do not lose energy, so you can use that as a measure of the initial jet energy. And you see the suppression of the away side jet, and the suppression is also by factor 5. So under the jet collaboration, so what we did is that we look at all kind of there's a different models, I should say, that implementation of this energy loss model into the jet production cross section. This is, I don't want to get into the detail, but essentially we survey all the model calculation and then fit the spectrum, the suppression of the spectrum of leading charged hadrons here. You will essentially trying to do the chi-square fit, and here we get the jet transport coefficient, the Q hat. Oh, by the way, if there's any question, you can stop me anywhere. Okay. How much time? How am I doing with my time, Igor?
You have about you've done about 40 minutes.
40 minutes.
So
Okay.
About 20 minutes or so.
Sure. So I will speed up a little bit right now here. So what happened? So what you see that we essentially determine the Q hat here, and we combine the data from RHIC and from LHC. Okay. So if we want to do that, there's another point. I mean, LHC has a couple of different energies here. At this time, there's only at 2.76 TeV colliding energy. But essentially, what we conclude is that this Q hat is about 1 GeV square per Fermi at weak energy, and is about 2 GeV square per Fermi at LHC energy. So apparently, the initial temperature, of course, created in the center of heavy ion interactions at LHC is higher than at RHIC. And here we plotted this as a function of temperature. It is rather flat, above 200 MeV here, and we don't know how to measure that in between. In the in this case, during the phase transition here. But we know that, as I will come back to this later, we know that Q hat from cold nuclear medium is very, very small. So in fact, this is about 100 times bigger in quark-gluon plasma than cold nuclear matter. I will come back to this when I discuss about jet physics in cold nuclear matter. So the jet and the density is so high at LHC, And the jet quenching, I mean, and also the energy, since the colliding energy is very high, the production cross-section for the jet is also very, very high. So it is, the jet quenching is so apparent, you can simply see that from this, what we call a Lego plot. You find that in PP, there's, normally you produce two jets. Here is a Lego plot, this is the phase distribution of the two jets. Eta here is the rapidity direction. So we are looking at the central rapidity, and this is the azimuthal angle phi. And normally two jet is produced back to back. So normally, they are back to back in phi angle, azimuthal angle. You see these two jets standing out in PP interaction, but in heavy ion interactions, if you find one jet here, and the other jet is completely gone because of the jet quenching here. And this is the Atlas measurement. They published the first jet quenching paper from LHC. They really do see this enormous jet asymmetry here, which means that asymmetry means you have one jet and the other jet energy is very small or is simply gone. But here, this jet is different than leading particle here. This jet is, in experiments, you construct this jet by looking at a cluster of hadrons within a cone, and then you subtract the background. But that is very tricky in heavy ion interactions, because we know that the jet loses energy into the medium. But in this case, the medium, where does the energy go? It cannot really disappear because of energy conservation. So in this sense, that the medium is essentially the energy lost into the medium will become a medium excitation, but the medium excitation response could become part of the jet within the jet cone. So in order to study this, you really have to consider the medium excitation and then the contribution of the medium excitation within the jet cone here. And so the simple idea is, if you look at hydrodynamics, you put a little bit energy into your quark plasma, they will produce a Mach-cone, and this Mach-cone, excitation will become part of your jet. So to do this, we have to develop the jet transport. You really have to look at the multiple interaction. You not only have to look at the jet energy loss, but you also have to look at how the medium is excited here. So, for example, you look at the jet transport. So here is a model, what we call linear Boltzmann transport model. You simply describe the jet transport with this Boltzmann transport. You not only look at the jet energy loss, but you also look at the recoil from the medium. And this recoiled medium will interact with the medium again. And also the radiated glow will also have to interact with the medium again. And then you do this within a dynamic evolution of the medium described by 3+1D viscous hydrodynamics. And in another extreme, you can, if you believe that all the recoil partons, when the energy is too small comparing to the temperature, for example, and you don't trust perturbative QCD anymore. And so here is another extreme. We call it coupled LBT. So you simply just do your jet transport, Boltzmann transport together with your hydrodynamics. And then you consider the recoil partons below this scale is completely thermalized with the medium. And then you put them in as a jet, as a source term feed into this hydrodynamics. And you run this, together. So here I give you one example how it will look like. So here we consider a jet, a photon plus jet. So here is a process that a photon is produced together with a jet, and because of the momentum conservation, normally photon and jet they are back to back. So here is the early stage. You have a photon traveling in this direction, you have a jet going to this direction, and you run this coupled transport together with quark-gluon plasma, and later on, and you can almost see with your eye here, there's some kind of medium excitation here because of the jet medium interaction here. So to see that clearly, we run the hydro twice. We run the hydro with the jet, and we run the hydro without the jet with the initial bulk, initial condition. And then you simply subtract this. And on the panel, on the right panel here is what's left over. And there you indeed see the medium excitation here. You see the shock wave, in the jet direction, but you also see a diffusion wake behind the jet here, which essentially the depletion of the medium. It looks like if you ever on speedboat, you see this. You see the shock wave in front of your boat, and if you look behind, and there's a diffusion wake. Okay. So to do this, then when you look at the jet physics, you have to really look at this all together. And so here is the final calculation. You look at the for given photon energy here the jet photon energy is 8 GeV, for example, or it's better if you look at Z boson for given this here jet boson is 60 GeV here, and then you look at the jet energy distribution on the way side. Normally they are balanced and not exactly balanced because there is initial radiation, but it's roughly balanced. Here, that's why you see the peak here in PP interaction. But in heavy ion interaction, given by the red line and dot, the data point and our calculation here, you really see the energy loss of this jet. This is a gamma jet, this is Z jet. So and then here I want to emphasize the importance of inclusion of the recall when you do this. So if I calculate the jet energy in my model calculation, I calculate the energy loss by including this recall pattern or not. And you can see that the energy loss is reduced quite significantly. That's because some of the recall pattern will end up with they will travel outside, jet cone, you have an energy loss, but some of them still remain in the jet cone. They will not contribute to your energy loss. So if you don't include this recall pattern when you do the calculation, you miss part of it. And and we also find, in addition, you also have to take into account the diffusion wake, and also this energy loss will depend on jet cone size, and will be also sensitive to the radial flow here. And by taking into account all of this, so you can describe the suppression of single jet quite well, at both energies at the LHC here. So now we are looking at more detail here. So if you have a non-central interaction, so I think if you have heard talks about heavy ion interaction, you know that this non-central interaction, the quark-gluon plasma is not spherical, but rather it's a cylinder. But the cylinder is the cross-section of cylinder for non-central interaction is a football-like. And the bulk, in this case, the bulk itself the momentum coming, the hadron distribution coming from bulk definitely will have anisotropy because the expansion in this direction will be different than in this direction, in the in plane and out plane. But if you consider jet propagation, the jet propagation in plane will be also different than the out plane. And definitely you would expect more energy loss in out plane in this direction than in plane here, in the short, because it travels through less material. and you do see the oscillation. If you look at, so in this case, if you look at azimuth angle distribution of this jet, you do see this modulation as measured by this I think Atlas. And then our calculation also give you, the same thing here. And we know that one way to categorize this is by looking at the second order coefficient, or second or third order coefficient of this azimuth angle, and you get this what we call elliptic anisotropy, V2. And indeed, V2 as function of PT is non-zero, definitely non-zero, even at very high energy. If you go to even 500 GeV jet, is still non-zero because of this. And more, in this case, this is our theoretical calculation here. You can do event by event measurement or calculation here. In each event, you know the bulk V2, which essentially categorizes the initial shape of the matter. And then you can calculate or measure the jet V2. And then indeed, you can here, this is event by event calculation. The jet V2 is almost linear is proportional to the bulk V2. It's almost linear here. And this is what we call the soft and hard probe versus of soft medium here. But this so far I think has not been measured yet. I hope they will measure it pretty soon. Okay, so finally, and then you also wonder where eventually the sum of the energies lost will go out. You are coming out of the cone here, right? So here you can look at this by looking at the jet shape. The jet shape is essentially you look at the jet with a given cone size, and then you look at the energy distribution within the jet, how it is distributed along this jet cone here, as function of this jet radii here. And then you measure the ratio of the jet shape in heavy ion interactions versus divided by pp as a baseline. And you can see that it's enhanced as you go through the cones, the edge of the jet. And the enhancement is mostly come from those RHIC, the medium excitation or the medium response. And in fact, if you go beyond the jet cone, this enhancement is enormous. So that's where you study the jet response, the medium response of the jet. And then you can also look at the particle distribution in the response. And we find that enhancement comes mostly for soft particles here in this region. Okay, and this is what we call fragmentation function, and QCD essentially is the ratio of hadron momentum divided by the jet. Here is the gamma. Okay, let me come to the end. Looking in the future here. So we are looking at electron-ion collider physics. As I have mentioned already when I discussed about the temperature dependence of the Q head. And you can do this. You can apply the same idea of the DIS, deep inlet scattering of nuclei here, by looking at the suppression of the leading hadrons here. And from there, you can, this is measured by Hermes experiments, for example, at DAISY, or for electron, xenon, krypton, scattering here. And you look at the suppression of leading hadron, and they are really suppressed. By feeding this data, and we find out that this Q head inside nuclear medium, is only 0.02 GeV squared per Fermi here. So if you compare, remember, if you compare to that in heavy ion interactions, which is 100 times more. So that tells you how hot and dense the quark-gluon plasma is. But there is something more we can do. Okay, so here is our recent study. So if you look at the dijet event, and this induced radiation process, large angle and large transverse momentum, we calculate this. Okay, so essentially you look at deep inelastic scattering, but with two energetic particle or jet with given angle. You can and here we calculate the medium modification of that because of induced radiation here. But here you definitely, this cross section, this angular distribution depend on the initial transverse momentum of the quark, and it's here. It also depends on transverse momentum of the glue, that's glue transverse momentum distribution here. And there's convolution. So the final transverse momentum of the quark and the transverse momentum of the glue should be the same as the initial, because of the transverse momentum, momentum conservation here. And then if you, for a fixed value of the transverse momentum of the glue and the quark, and then you look at the angle, so then you can actually probe different region of the transverse momentum here. Okay, and they are constrained because the value here of initial quark and of the initial glue are constrained because of this. So here is an interesting plot here. So in this case, we are looking at fixed transverse momentum of a quark and the glue jet. And then you look at the its cross-section, this medium modified cross-section as function of the azimuthal angle. And you can see clearly this is the peak structure here. Okay, this peak essentially is because there's overlapping region, is because of the overlapping region of initial quark distribution versus the initial glue distribution when their momentum is constrained. So by looking at this angular distribution, you actually probing the transverse momentum dependent Parton distribution function in your medium, and which is one of the very important quantity what we want to look at EIC. And in addition, because of this, there's still LPM Landau phenomenology of interference within this amplitude here. You find that this cross section has a quadratic dependence. The modification has a quadratic dependence on nuclear size. And if you measure this, you actually see the LPM interference in the dijet cross-section here. Okay, I think I probably ran over my time, and here is a summary. So jet quenching has been used successfully to study properties of quark-gluon plasma. And we have extracted jet transport coefficient, and that is a lot of work to do in that direction, because we want to have more we want to have more precision determination, and also we want to look at the energy dependence, the temperature dependence, and jet quenching and the modification of dijet, for example, in EIC can also provide us also very important information by nuclear Parton momentum, TMD Parton distribution. So finally, I want to thank my collaborator here, my San, and also the Chen Wei, Yayun, Luotan, Longgang, Yuan Yuan, and then the funding from DOE, NSF, and NSFC. Okay, thank you.
Well, thank you very much. That was very nice. A lot of material. I probably didn't digest everything, but there were a lot of interesting things said. So let's go to the questions now. We have at least two people who are trying to ask questions. I think Giorgio was first.
Thanks. This is sort of in your introduction, in your really nice introduction, when you talk about the difference between QCD and QED.
Yes, yeah.
Yeah, this is a silly question. If you go to the transparency, sorry, sort of for my ignorance, but this is very interesting. I mean, when you,
yeah,
usually, yeah, this one.
I go too fast.
Sure. To limits, yes. LPM interference.
Yes, here, right?
Yeah, this one, yeah. This is sort of, usually when people look at courses in the introduction of QCD, the plateau is introduced as being, you know, the Feynman model, which is ultimately because of asymptotic freedom, right?
Yeah.
Partons are distributed uniformly in X, and so on and so forth. Here, what I find really interesting is that you derive the flat rapidity. This is purely tree level. This is a purely tree level calculation. It knows nothing about asymptotic freedom. It knows nothing certainly about, you know, confinement partons or anything else. I guess it basically comes from the fact that gluons are massless and there is no mass scale, and in QED there is a mass gap or something like this. I just wanted to comment because I've never seen, this is my ignorance, but I've never seen the flat rapidity shape derived just from tree level scattering considerations.
I think this is for me, I mean, this is well known from the beginning, and the first calculation from actually go back to George Birch and Jeff Gagnon, their paper, and they actually in that paper they demonstrate this plateau really coming from this tree level.
Okay.
Yeah.
Okay, just
yeah, and then the another factor is, of course, you know, the glue does not have mass here, and the quark's mass is negligible. If you introduce a heavy quark, for example, and then the angular distribution will be different, and that will then you start to see the suppression in the middle again. There is that cone effect.
Okay.
Okay. We have a question from Thomas Schaefer. He asked me to ask on his behalf. So modern values of Q hat are quite a bit smaller than the result from 10, 20 years ago. For example, Phoenix 2008 claims Q hat to be 13 plus minus 5 GeV squared per Fermi compared to the modern value of Q hat of about 1, 2. Is there a simple explanation of that?
I think that's essentially there's two facts why the phenomenology converge. First one is the theory have improved. I mean, because there can, you know, different. We look at all different models, and this high value of a Q hat. The Thomas referring to is, I think, coming from one model calculation, and that model calculation has since actually been revised, and the end of that calculation essentially converged with the rest of other model calculations. And the second one is that now there is more data. If you combine RHIC and LHC, now two energies, you have more data, so that give you more constraint through this chi-square fit.
Okay.
And so far, this has been this one has been improved lately, and this is like almost 5 years ago. There are new calculations with using Bayesian analysis through global fitting, even with like temperature dependence put in. But more or less within error bar, they still agree with this first attempt.
Okay, thanks. Shangdongji?
Yes.
Hi, Xiangdong.
Hi. It's nice talk and learn something. So I have a question about in the cold nuclear matter.
Yes.
You know, when you have a nucleus, but of course the nucleus is very dilute. Because I remember that the average distance between nucleon is pretty large.
Yes.
And so you can imagine how to completely fill the nucleus with, not like in the neutron star. That is when the nucleons are very, very close. In this case, I would imagine this Q hat will be increased by, I don't know what factor, maybe factor 5, something like that.
In the neutron star, I mean, what do you mean?
If you come close pack the nucleons.
Yeah.
Then you would get, imagine the whole nucleus is just like inside of nucleon. And then you would get Q hat would be presumably multiplied by the ratio of the nucleon volume versus the nucleus. So you would have an increase, but that increase is not sufficient to explain the difference between the cold matter and the hot ones. Probably there is another order of magnitude. But in terms of energy density, I think inside the nucleon, the energy density is fairly high. So there must be some kind of thermal effects to that. So I'm trying to understand the difference between this number. I don't know how accurate that is. Maybe the way that's been extracted is not reliable, and there's no error bar on this. I wish that there's a better statistics on that. Well, better accuracy on this number. But if that's true, that I think we need to understand what is the difference from the hot ones. And so do you have any comments along that direction?
Sure. Well, this is a good point. First of all, the Q hat, if you look at the definition of the Q hat, which essentially is proportional to the local, the Q hat is a local quantity, okay?
Mm-hmm.
It depends on the local glue density,
right?
Okay. It does not only, for a nuclear, for example, for a cold nuclear, it not only depend on the nucleon density inside nucleus, but it also depend on the glue density, glue distribution within the nucleon. Okay.
Mm-hmm.
And I think indeed this, if you compare, even though you still consider that nuclear is really packed, right? But if you count the number of gloom density, you just calculate, it's still far more smaller than the quark plasma at above the phase transition temperature. It's far more.
Is that proportional to the energy density?
No, it's not proportional density. As I said, it's proportional to the glue number density inside.
Yeah. So what I'm saying is glue number density proportional to the energy density or not?
The glue number density, in the quark plasma, definitely yes, because the higher temperature, the higher energy density, the larger the glue number density. But I'm not quite sure I think maybe in the cool nuclear is similar, especially if you vary. For example, if you vary your scale of your probe, you go to shorter and shorter distance, and then the glow density, of course, is higher and higher. The energy density is higher. But I want to point out the difference here. Here in this particular calculation, we are looking at the quark scattering with the glow. These are rather at very large x. Okay, it's not a small x.
Mm-hmm.
This is a very large x. Mm-hmm. And concerning the uncertainty of this extraction, I just give this. This is a very old. There is a recent, very systematic analysis of the PT transverse momentum broadening of cool nuclear inside cool nuclear. They combine. I mean, by Zhongbo Kang, Hongxi, and their collaborators. They look at all the data available, like DIS, like Jie-Psi PD spectrum, like Xin-Nian. They did this the whole systematic analysis, and they come up pretty close to this value with plus minus sign. I should have quote that paper. So they are there. If you want more precise, they have in that extraction, they have plus minus error bar there.
Mm-hmm.
Okay, that's good. I don't see other questions from the audience. I did have a question of my own though. Somewhere around page 31, you were talking about V2 at very large energies of the jets, the jet V2. I was kind of surprised. Is there a simple way of understanding how is it possible for jets with such a high energy to developing a substantial V2? Physics-wise, it seems very unnatural.
This is the difference between the jet and a single hadron. Okay, a jet is not just one particle. This is my understanding. The jet is not just a one particle. It has many partons inside the jet cone. And at a certain point, when they become incoherent, those partons will scatter with the medium, and therefore transport energy outside the jet cone. Okay, so in this case, this is the reason why this is similar. This is the reason why this, for example, suppression here, you don't see the disappearing or suppression. You would imagine this is quite contrary to if you look at a single hadron. Single hadron essentially is coming from leading parton. The leading parton, when its energy is very high, the energy loss is becoming negligible. So you would imagine that this ratio here go up to 1. But not for jet. Not for jet. You still see suppression of 40% or 50% suppression at almost 1 TeV jet energy. And and for that same reason, you should also see the V2 here.
Okay, I guess I'll have to think about this a little deeper, but I see roughly what you're saying. I think we have another question from Hong Yi.
Hi, how are you? Yeah.
Oh, hi.
Yeah. So I have a short question. So you mentioned a few models, theoretical models of this jet quenching, like this PDMPS and Amy and higher twist. I suppose that they all belong to the kind of bigger category of LPM physics. Could you explain exactly what is the point of difference between these models?
Okay, this is a model essentially. I mean, when you calculate this, okay, when you calculate the jet quenching in your model, there are many things involved. The first part is that how do you model your medium, right? Well, how do you model your medium? For example, in this particular in this slide, there's Martini, for example. Martini, this model is based on this AMI formalism. The AMI approach consider the quark plasma is in a thermal system. They used the finite temperature field theory to calculate the energy loss. Versus GOV is consider the medium is sort of like consists of many partons, but each of them is like act as a static potential scattering. And there they only consider like they do expansion. They only consider like the leading order in opacity, which means essentially they only consider double scattering, just one or two scattering. Instead of in AMI, and for that matter, for BDMPS, they consider many soft particle scatterings and one emission. Okay, so if you this is all different implementation. If I want to categorize this, divide this to essentially one is AMI or Martini here, and also BDMPS. On the other hand, is high twist or GOV is few scatterings, and BDMPS is multiple soft scatterings. And there is one study actually calculation some time ago. They claim this is a sort of exact calculation. In fact, it can interpolate between this GOV and BDMPS limit. Ideally, one should implement that, but somehow that's difficult to do at this point. So that's essentially the difference between these different models.
Okay, I understand that's about it.
It sounds like that.
Go ahead.
Yeah.
I think we lost the sound from Hongyi. I think we don't have anybody else with questions, so I think we will be wrapping this up. I would like to thank you once again for taking your time preparing the talk. It was very instructive. I learned a lot. There was a steep learning curve, I guess, but still, I learned a lot. I probably will say from everybody else that was very nice, and thanks on behalf of everybody.
Oh, thank you.